Welcome everyone to the final session of day 2. Just as a reminder that we were doing a sort of more rewriting or hypergraph themed day. Yesterday we had a more binary algebra themed day. Tomorrow we'll have more of a tensor or hypermatrix proper themed day. So our final speaker is Francesco Lotito. As you can see from the screen, he is one of the developers of HypergraphX, and at the Wolfram Institute, we're very excited to have you here at last, as we had some chats last year in Vienna in the Network Science Conference, and I think we are one of the few people in the world who are busy trying to get software to rewrite hypergraphs and do some nice analysis of hypergraphs. So it's a delight, and the floor is yours.
Thank you, Carlos, for the introduction. Thank you for inviting me here for these talks. So yeah, my presentation I think is a bit different in the sense that I'm present mostly something that is very hands-on, like a Python library to deal with higher-order networks and hypergraphs, and I will briefly give you a background on the more like theoretical and physics-oriented background, and then I will dive into like some like tutorial and examples on how to use this library. What are we developing? What are we developing also in the next future? So I wanted to start like spending a couple of seconds telling you like a brief introduction to networks. So we know that a lot of real-world systems can be usefully described by using networks because they are made of unities that they interact. Of course, networks are a good model for this. And we have examples of these systems of interacting unities in a lot of domains, from social networks, because we have people communicating, exchanging mails or being friends on Facebook and so on. But we also have networks on, like in biological domain, from protein-protein interaction to neural networks, and of course also other artificial systems such as co-authorship networks, co-citation networks, and web, and so on. So the idea is that we want to understand these systems, and we usually mean for understanding systems some common tasks, for example, ranking nodes in a network, so understanding what are the important nodes for some definition of importance. We usually want to perform clustering on nodes, so understanding what are groups of nodes with similar characteristics or that interacts a lot in the nodes, and less frequently with nodes outside their groups. Or usually we are also interested in the dynamics on networks, so how things, let's say, move over a network, for example, spreading of a disease, and trying to understand this dynamics on networks. I usually focus more on the structured networks because I have a background in computer science, so I'm more oriented in studying the structure of graphs and so on. So we used a lot of these tools from mathematics, like graph theory and so on, to understand real-world systems using graphs. But and this is fundamental to understand why we are talking about hypergraphs in this context, is that nature is not that simple, and sometimes graphs are poor representation of some systems in the real world. For example, we want to understand the direction of an interaction because it's fundamental for us to understand if a node A sent a message to node B, or if node B sent a message to node A, and we need to put somehow an arrow to the interaction. So we want to remember what was the direction of the interaction, and we cannot use like standard graph for this because graphs are just vertices connected to each other, so just lines. So usually we complicate things by adding a direction, or adding some labels to the edges, for example, labels that capture the intensity of an interaction or the temporality of an interaction if we want to understand, I don't know, if an interaction occurred at 4 p.m. or at 4:5 p.m. or at 4:30 p.m. But sometimes can be useful also to encode the modality of an interaction. So, for example, if I send you a message on Facebook, is different than if I send you a message on WhatsApp or if I send you an email. And to understand some system, it can be interesting or can be sometimes fundamental to encode more information. So to encode this information, we have more sophisticated mathematical objects. We use directed graphs, so edges are now allowed to have a direction. We can use also weighted graphs in which edges are allowed to have a weight, or temporal graphs, so edges are allowed to have a temporal label, or multigraphs or multi-layer graphs in which edges are allowed to connect the same nodes but being discriminated by a label, so having the same edge repeated a lot of time but with different labels. So the general theme of network science in this context is we want to capture more information about the system we want to understand, so we use more complicated mathematical objects because we get more expressive power, so we can capture more things about the real world. But of course, we pay the cost of having a more complicated model. We have more complicated algorithms, more complicated software, of course, and we need to cope with this increasing in the complexity. And so there is this sort of balance. So we want to capture more things, but we pay the cost of having a more complex model. And sometimes it's also not that useful to have a more complicated model if we don't get that much in as a return. So it depends on the system we want to study. But there are systems that benefit from this more like sophisticated models. So as of now, we were discussing only about pairwise interaction, and pairwise interaction are very common in the real world, but they are not the only kind of interaction that we can have. And group interaction, and by group I mean multiple nodes that are active at the same time and they are interacting at the same time. And this can be very common in the real world. For example, authorship networks are made by group interaction, in the sense that we have nodes that are the authors of our papers, and the interaction are the papers. So multiple authors write a paper at the same time. We can also have other example of affiliation networks. For example, I don't know, people buying some stuff online, so an order could be made of multiple objects at the same time. But we can also have some example of prey-predator networks that are like made by group interaction, or also examples from biology where we have complexes of proteins. So in nature, it's common to have also this group interaction. And going back to what we said before, sometimes we want to capture in our models also this complexity. And this can be very important to capture this complexity because, for example, I wanted to give you this example in which I have multiple parties and people going to parties together. And we noticed that if we want to model this system with traditional networks, so traditional graphs, and to model with traditional graph, we need a binary relation. So we can use a binary relation, for example, went to a party together. We get these very complicated graphs in which we cannot really reconstruct anything from the original structure of the parties. And so what we do is we move to, as always, to another mathematical object that is now able to encode this group interaction without losing information. And we use hypergraphs. So hypergraphs are a generalization of a graph, of course, in which we have vertices, but now interaction edges can involve multiple nodes at the same time. Yeah, they are not limited to pairwise edges. Okay, so each hyperedge is of course defined as a non-empty set of nodes. Of course, graphs are just like a particular case of hypergraph in which each hyperedge has cardinality too. And we notice that now our party system, let's say, can now encode it without losing information using a graph, because each party, so party 1, party 2, party 3, which is made by a number of nodes that is larger than 2. So we have Sarah Ross Anderson for the first party, we have Sarah Ross Drew Elliott for the second party, Ross Elliott Keith and Ellison for the third party. So we have like larger set of people participating to a party together. We can model with hyperedges this party, and we encode like the right amount of information that can be useful. It depends on our task, but at least we know that we have all the information available and we have encoded it into an hypergraph. Instead, in our graph, we notice that we lose a lot of information because we cannot even recover the number of parties that we encoded if we consider only our plain graph. So we know that, for example, Sarah and Ross went to a party together, but we don't know what other people were together to Sarah and Ross at the same time. So, but in our hypergraph, we are able to recover that information. So we call this higher order networks because we want to encode these group interactions. And usually me and my group, we work a lot on hypergraphs. So we use hypergraphs to model these systems. Of course, hypergraphs are not the only way to represent group interaction or higher order networks. In the past, we used a lot bipartite graphs to model this situation in which we have nodes representing the actual unities of the systems, and also we have other types of node representing the interaction. So we could link like group interaction to nodes using like a lower order representation of using a graph. Another popular tool is simplicial complexes, which is as you know, a very established mathematical framework from algebraic topology. And it's also very common to use simplicial complexes to model group interaction, so to encode group interaction from the real world. But the problem, I mean, not a real problem, but like an assumption, is that we also have the closure with respect to phases by definition. And in some physical system, for example, people meeting face-to-face interaction, this assumption can be very restrictive, because if we have, for example, a group of size 3 of people talking to each other, it's not. It's a bit restrictive to say that also we have all the other interaction of size 2 existing in the system. Sometimes we can use simplicial complexes without worrying that much. Sometimes they have this limitation. So in my group, we focus on hypergraphs that we believe are the more flexible tool, and also like more oriented to my background in computer science. Instead, simplicial complexes is more like popular in the mathematical community in network science. And of course, we have more tools that can be also sometimes efficient from a computational point of view, sometimes not. Sometimes they can useful for some tasks. So we have the tools from algebraic topology that can be useful. So we don't discard simplicial complexes, but like we need to choose the right model for our system. In the case of bipartite graphs, this is interesting because in the past we used a lot bipartite graphs to represent higher order networks, but to like in modern network science, let's say, we prefer hypergraphs because traditional problems are better represented on hypergraphs than bipartite graphs, and also like the generalization is easier sometimes, going from like graph network definition of problems to hypergraph hypernetwork definition of problems. But bipartite graphs and hypergraphs are more or less equivalent from like modeling point of view when representing real world systems. So just to summarize a bit what we said so far, we used a lot of networks to represent real world systems so far, and networks are made by dyadic links. But then we realized that networks would be like a not so good model for some real world systems. So we added a lot of complexity, considering direction in the interaction, weights, temporality, and the type of the interactions. But some years ago, we realized that also we wanted to study and to encode explicitly the groups, and consider also not only pairwise interaction, but also considering groups without relying on lower order representation networks, but encoding directly groups. So we started to use more sophisticated mathematical objects, such as integer complex bipartite graphs. And I want to stress again, in my group, we use a lot hypergraphs to model this complexity, to deal with this complexity. And the key takeaway is that, as always, we gain more expressive power using these tools, because we encode more information. But we need to pay the price of having to deal with more complexity. So we need to develop new algorithms. We need to develop more complex statistical tools. We need to develop new also software. So I wanted to highlight this review. One is more like a general, one is one focuses on the physics of higher order interaction. They are very interesting to have an overview of the field. But in the latest years, the number of works dealing with hypergraphs exploded, or higher order network exploded. So we have like a lot of interest in this stuff as of now in the field of network science. So the field is really hot, and in like this huge amount of work, we also wanted to stress about the importance of having like a software to manipulate and analyze this hypergraph data. And of course, like software are really important. Think, for example, about the importance of Network X or other tools that we have to deal with networks, that without these tools, it will be very, very difficult every time to re-implement everything that we need for our work. So we believe it's very important to have like a set of developed tool, open source tool that you can easily use. But dealing with hypergraph in the software domain is not that easy, because it's not trivial to understand how to store hypergraphs in order to perform computation. So what data structures should we use to implement hypergraphs? But also it's very hard. Other simple tasks that on network can be more simple. For example, it's hard to visualize hypergraphs, and it's also very hard to design algorithms on hypergraphs and make them efficient, especially is very, very, very hard. Another thing that is very important is having data that you can analyze, and you can like benchmark your software solution or your new algorithms. And it's very important to have a set of data already made and easy to use. So we tried to put some effort in this case to develop a library to deal with hypergraphs, with the idea of having a set of tools to construct, visualize, and analyze hypergraphs that should be made open source, of course, so people can contribute to use our stuff and build their scientific work on top of that. We want, of course, to make the library very user-friendly and accessible. So we made a lot of tutorials to use our framework. So every time we have some paper implemented using HypergraphX, we try to have like a tutorial to use our new tools in the library. And of course, we wanted to have a repository of data. So now I want to get a little bit hands-on, so how to install the library, how to use the library, so to have like an overview of what you can do with HypergraphX. So let's start by the intro, the installing the library, which is very easy. We tried to make it very easy, so you can install using pip in Python. And of course, you have like very basic functions. So you can create an hypergraph. So giving nodes and adding edges is very easy. So you have this hypergraph object, and you can add through list nodes and edges. You can of course add the weights, and you have functions to get the edges in the hypergraph, to get the weights. Should be very easy to perform this basic operation.
Francesco, just one question. Are your edges lists by default in terms of the data structure? Are they ordered or unordered by default? Can you?
Yes, they are sets. So yeah, there is no order in this case. So basically, we in whichever order you put the edge, we let's say store it in a way that it's unique. So yeah, it's stored as a set basically. So as of now, we don't have like an ordering on like by default we don't have an ordering, but you can also impose an ordering on the edge. You have a parameter, but in that case, like for example, if you have an edge 1,3, it will be different from an edge 3,1. So you can set a parameter, but by default, the edges are unordered. But I think I will discuss a bit later on in this sense, because it's a bit more, we are working a bit on this, so yeah.
And you
yeah.
And you implement everything in Python, right?
Yeah, everything is in Python, yes.
Okay.
So you have some also basic operation, like I can query the hypergraph and say, oh, is the hypergraph connected? And you get false or true, like this basic operation on query operation on hypergraphs in the similar way that you have on network X, for example. We are working a bit also on the drawing hypergraphs. So for really small hypergraphs, this can be done, but for larger hypergraphs, this is a mess. We are working on this, but it's not easy. But for the purpose of this tutorial, we can also visualize our hypergraph. So we have like our hypergraph that is not connected. So, but we can also add edges to the hypergraphs and for example, here we add a new edge that connects the two connected component, and we can draw it again. And now the hypergraph is connected, of course, just to give you some example of what you can do. We also spend some time in having this metadata associated to vertices, which can be useful in real-world analysis. So, for example, you can add some attributes to the vertices. For example, here I added an attribute role to node 1, and I mentioned that the role of node 1 is being a student. So now I can retrieve the metadata associated to nodes, and I get that object 1 is a node and has the role of a student. Another package that we have, like basic package, is generating graphs and hypergraphs. So for example, you can generate random hypergraphs. So you specify the number of nodes and the number of edges. And if you specify also the number of edges for each cardinality. So I want like 5 nodes in cardinality 2, 5 edges in, five edges of cardinality 2. I have 2 edges of cardinality 3. I have 2 edges of cardinality 4. So you can generate these graphs and visualize them. Of course, this is a random generation, but we also implemented some more some more complex generating models, so you can experiment with the generation of random hypergraphs with different algorithms. So I wanted to take like a real world example. So we use a real world data about interaction in high school. So we have interaction of different sizes of face-to-face interaction of different sizes. So interaction 3, 2 of size 2, 3, and 4. And experiment with some packages in the library, so we can understand like from like hands-on point of view what I can do with a real world data set. So we have, of course, this data. We have some different distribution of higher order degree for every interaction size. But something more interesting that I can do that on this package is performing motif analysis on this hypergraph. So I have like real world hypergraph. I want to understand what are frequent pattern of interaction in this large hypergraph. So by motif, I mean I select like a small number of nodes, for example, 3 nodes, 4 nodes, and I count the number of occurrences of each possible pattern of interaction of this size 3 or 4 or 5. So in this case, I selected 3 nodes, so I cared about patterns of the size 3, and I computed basically the occurrence of every possible pattern of interaction of size 3 in the dataset. So I have 6 possible patterns with 3 nodes, and considering both low order interactions, so the first 2 patterns, but also both lower order interaction and higher order interaction, so both interaction size 3 and size 2. And I have 4 possible patterns in the orange interaction. And yeah, we can count these interactions, these patterns, and we have different abundance scores. So basically, with respect to random hypergraphs, how much a pattern is frequent in my real world data. And we get that triangle are very popular. So pattern number 2 is popular in our high school data set, but also interaction like the simplex, let's say, made by 3 nodes and one group interaction of size 3, and the triangle. So in pattern number 6 is very, very popular. Also pattern number 5 is popular because we have interaction size 3 and lower order, 2 lower order interaction inside the group interaction. But for example, we see that a group interaction without any following lower order interaction inside is unlikely to happen. So people interact in group, but also likely interact also in a pairwise fashion in this face-to-face scenario. If you are interested in our paper, we explored more domains, and we see that this situation is very common in face-to-face domain. So we get these results also in a primary school data set, also in hospital data set, in which we have people interacting in an hospital, but also at conferences. So this behavior of people interacting in group is common in multiple domains, but in other domain is different. So we have different patterns in co-authorship data, for example. So another thing you can do with HypergraphX is performing community detection. So we have multiple algorithms to get communities that also like analyze both interaction size 2, but also analyze the hypergraph structure. So they consider group interaction. And for example, here we extracted 3 communities from our data set, and we see that how the communities are are structured. In this case, we used an algorithm that is able to get also overlapping communities. So nodes are not assigned to a specific community, but are assigned like with different scores to multiple communities. That's why we have the pie chart for each node. An important task, I believe, that in Hypergraph is very interesting is also to get rid of noise somehow. So we also implemented this paper from Federico Musciotto. Sorry, this paper here from Community Detection was from Martina Contisciani and collaborators. This one is from Federico Musciotto and collaborators, and we have like we try to filter interaction based on their statistical significance. So basically, we sparsify our hypergraph. So we start from a very dense hypergraph and we get rid of non-significant interaction. And so you can notice that we remove a lot of interaction. We get a smaller hypergraph that has only statistical significant interactions. And this can be useful, for example, in the visualization. So you have an hypergraph that is very complex. If you get rid from a lot of interaction, and you remain only with the important interaction, let's say, can be interesting because sometimes also algorithms are very inefficient on hypergraphs, and you may want to have like a smaller hypergraph and perform your analysis. Yes, I mentioned that visualization is very difficult on hypergraphs, and yes, we tried to visualize this high school data set, and it's not easy. In fact, to get this visualization, I had to filter a lot using our previous work from Federico Musciotto. I get rid of a lot of interaction based on their statistical significance as a definition from that paper. And yeah, I tried to visualize the data set, and I got this result, which is at least it's a picture, let's say, of the hypergraph. Of course, it's a mess because you have this group interaction that overlap a lot, so you cannot go that far in the visualization. We are trying to scale, so to have more nodes in the figure, more edges, but it's not that easy. So as of now, we settle for this visualization. Another thing you can do with HypergraphX is the dynamics. We have some contagion algorithms implemented, so you can play with this spreading processes on Hypergraph. These models are from this work from Jacopo Jacopini and colleagues. So you also have some like dynamics model for hypergraphs implemented in case you are interested in these other subfields of network sites. And something that we are starting to work on, that we have some work and we are implementing in HypergraphX is time. So we are also interested in assigning temporal labels to hyperedges. So encoding that an hyperedge is active at time 10 but not active at time 20, or that is active at time 10 and last for 20 minutes, for example, or 20 seconds, and so on. And so we also implemented some temporal measures for hypergraphs, mainly from the work of Luca Gallo and colleagues. But yeah, we are developing on this stuff. We are trying to have more general, more general hypergraphs as possible, also implemented in the library, and not only like static and undirected and so on hypergraphs in the library. So something very important Everything is also available as a Jupyter notebook, so you can play with basically every slide that I presented here. You have a notebook associated with it, so you can try every paper we implemented, every measure and package we have. And we are also working a lot on our collection of data. Of course, hypergraph data is not a lot, but since the interest is increasing, we are trying to collect every data set that we have available. So we have a lot of data for face-to-face interaction. We have a lot of data of co-authorship data, but we are also trying to expand to more to other domain, and we are also trying to expand both to have more general data set to have like directed hypergraph data, to have temporal hypergraph data, and multi-layer hypergraph data. So to have a direction on the hyperedges, to have a temporality of the hyperedges, and to have like a type of the hyperedges as we mentioned briefly in our background part of the presentation. So speaking about the direction of temporality and type of hyperedges, I wanted to briefly discuss about our recent work on multiplex hypergraph. The idea here is that you have a set of hypergraphs. Each hypergraph is a layer in this case, and all the layers share the same node set, but each layer encodes a particular type of hyperedges. So as we were mentioning, each type can be associated, for example, to a different means of communication, for example, sending messages on WhatsApp or Facebook, as I was mentioned before. On hypergraphs, we have more examples. For example, each layer can encode a different scientific subfield in the physics domain, for example. So you can encode nodes, authors as nodes, you can encode papers as hyperedges, but you can also encode that each paper has its own associated physics subfield. So you have multiple hypergraphs. We have some other examples, for example, like EMDB data in which nodes are actors, hyperedges are movies, and each layer is associated with a movie genre. You have high school data that we were using like in the traditional format, like standalone hypergraph, but you can see it as a multiplex hypergraph in which nodes are the student, hyperedges are face-to-face interactions, and each layer is a day of the week. In fact, the high school data involves 5 days of the week. So we can aggregate everything inside a single hypergraph, or we can treat day by day and having 5 different hypergraphs. We did this in a recent paper from my group. So I just wanted to mention some results. We have that here each vertex is, for example, a physics subfield or a movie genre or a day of the week. So each vertex is a layer in the multiplex hypergraph, and we connected layer, and the larger the connection, the darker the connection, it means that the two layers are similar in the sense that nodes in both layers share similar pattern of interactions in terms of their order of interaction. So two layers are similar if I have a node that is active in both layers and is active both at order 2, for example. So in both physics subfield, he wrote a paper with the 2 collaborators or 3 collaborators and so on. So we measure also this similarity in terms of the order of interactions. And also we were interested in the different patterns of interaction in terms of the size of the interaction. So we see that, for example, elementary particle physics has a paper of larger cardinality of authors with respect to, I don't know, general physics, for example. But also that in the movie collaborators, we have that on average, every genre tend to involve a cast of like from 10 to 15 collaborators. And instead, in the high school data set, since there is no reason that people change day by day their like overall patterns of interaction, they tend to like be every layers tend to be similar to each other. And we see this also by their hyperedge size distribution. We have that in high school data set, we have like very similar hyperedge size distribution across the days. Instead, this distribution can be very, very different in the APS dataset, so collaboration dataset in physics, or in the MDB data. So we can notice fields in which you have larger amount of authors, smaller amount of authors, larger cast, smaller cast, and so on. Another interesting analysis was to understand how the degree of each node was spread across layers. And we measured this spread using this measure called participation coefficient, which basically is a kind of entropy. So how spread is the degree across layers. And so we wanted to measure if a node is like a generalist or a specialist, which means that a node participates in a lot of layers, so publishes in a lot of physics subfields, or if it publishes in a like one physics subfield or two physics subfield, but not a lot. And so we get interesting results. So like people were effectively divided in different classes of like spreading of the degree. So we had specialist node and generalist node in the real data. And like going higher order, we wanted to understand if also the hyperedge is connected like more generalist node or specialist node in the different layer. And we got that, for example, documentaries tend to be made by people making only documentaries, while family movies are made by people making like also participating in a lot of different movie genres, for example. Also in physics, we had that, for example, in nuclear physics, we had that people tend to be very specialized and participating only in paper in nuclear physics, while in other subfield, people tend to be like more generalist and connected in writing a paper in that domain. Instead, in high school, it's very trivial to see that like people tend to go to school every day. So every hyperedge basically links people that are always generalist because they participate in every day. Another analysis was like performing community detection layer by layer and measuring the similarity, the pairwise similarity of the communities inside each layer. And we got some histogram, like very hierarchical histogram, highlighting layers that had similar community structure and layers that had totally different community structure. For example, documentaries were totally unrelated with other layers. So while in high school, every day, I mean, the community structure was consistent day by day because people tend to connect with their friends and keep the same friends every day, basically. This measure really presented in our one of our latest preprint, and everything is also implemented in HypergraphX, so you can play with this and experiment. I think it can be promising to study new data set using this approach, because sometimes we lose information by aggregating everything in a single layer, but having multiple layers can give new insights on our data sometimes. And of course, multiplex hypergraphs are not the only generalization of hypergraphs that is interesting. Of course, we can define directional hypergraph So hyperedges are allowed to have a direction. So we have a group of senders and a group of receivers. As Carlos was mentioning, this is not the only way to implement direction. You can also implement direction in considering permutation somehow of the nodes in a set, so having an ordered set representing an hyperedge. As of now, we are focusing on this more like traditional network science perspective of having sender and receiver, but each data can be modeled in different way. We could model different aspects of our data, and it depends on our task what we want to encode and what we can discard as a complexity. And there are lots of data in which this can be useful. For example, I can send a mail to multiple people at the same time, or for example, we have some data set about Bitcoin transactions. So multiple wallet can send money to multiple wallet at the same time. So having a more complex structure of interaction in which you have multiple senders and receivers. Again, you can have temporal hypergraphs in which you assign a temporal label to hypergraphs and you have a structure that evolves in time. And basically, you have the same story again. You can add more complexity. You can encode more information. Of course, you pay, again, the price of having more complex model, and you need to develop new algorithms, new tools, and so on. And a question that I'm trying to answer, or at least I'm trying to answer for specific data, is it useful to have these more complex models to analyze this data? And it's not clear the answer to that, in the sense that we are developing new models, we are developing new tools, and to encode more stuff. And sometimes it's useful to encode more stuff. Sometimes, basically, you can settle for more basic models. Even you can settle for traditional like networks in like graph theory sense. So yeah, it depends on the data. There are data sets in which I think it's fundamental to have like an hypergraph structure and possibly more general hypergraph framework. For example, an easy example is co-authorship data, in which papers are by design, like papers and authors that write papers together are by design an hypergraph, and using graphs is like leads to like losing a lot of information. So we are going on this line to understand what are the domains and the data set that really benefits from an hypergraph representation. And that's why having like ready libraries, I think it's useful, because it allows people from application domains to easily play with hypergraphs and understand if they get more than like a traditional network framework analysis, let's say. So we are waiting for people to use our software and see what they can do with hypergraph, and if they get more like some nice insights on their dataset. So I think this question is really important, because we don't really want to developing new tools just for the sake of developing new tools. We want to developing tools that people actually use. So I think it's important to remember this stuff when like doing this kind of research. So like before closing this like small talk, I want to thank all my collaborators, because of course having like designing a library is a whole lot of effort. So I was not alone in this. I had like a very huge amount of people collaborating and implementing their paper using this library. So I have Martina Contisciani, Caterina De Bacco, Leonardo Di Gaetano, Luca Gallo, Alberto Montresor, Federico Musciotto, Niccolò Ruggeri, and Federico Battistone. So this is it. I hope it was interesting that you could now play with the library. Of course, we welcome feedbacks and discussion. And of course, we are open to contribution because the software is open source. So yeah, we usually accept pull requests and people contributing to the library if they want to. So yeah, thank you very much for the attention. If you have any question, I will be happy to answer.
All right. Thank you very much, Francesco. Any questions from the room here?
So thanks for the nice talk. So I would just try to get this started again. So you're saying in social or in network science, let's say, for example, I'm looking at a Facebook graph, I get some data, and it seems there's a design choice. Either I immediately code some substructures into hypergraphs, or I stick in the beginning with you were trying to explain the difference in practice between using a hypergraph versus using just a bipartite graph, right? And it seems that you are saying for some applications at least, it's useful to use it. Maybe if the information is anyways and always linking to 3 people or always to 4, then runs a bipartite graph, just use a hypergraph. So at least I'm keeping track which 3 people. But I mean, is that really such a conceptual difference than using bipartite graphs? I might have missed the point, maybe.
No, they are actually the same. Actually, for example, in my library, hypergraphs are implemented using bipartite graphs.
Exactly. Yeah.
So it's not like a conceptual different, but like I think there is no difference in these 2 objects, but usually problems are stated better using hypergraphs in network science. That's the only difference.
Just one question, because now then later in the talk you had sort of analysis of a data set then by counting number of certain kinds of patterns, but now we hypergraphs. And one of the things that I find interesting, because I mean, actually bipartite graphs and hypergraphs are not at all on the same footings as data structure when it comes to manipulating them. So basically with a bipartite graph, there's no problem. I mean, if you have some entity which codes for a vertex, let's say of type A, which let's say is an actual person, and then an entity of a vertex of type B, so the other type is a group, then there's absolutely no problem adding to a bipartite graph another person to a group. This is a perfectly legal operation I can take. I simply add a new edge of type A goes to B, right? While with a hypergraph, I would have to retract the original hyperedge, let's say with 3 members in the group, and create a new one with 4 members in the group, correct?
Sorry, I didn't get really the question.
I'm trying to model a process where I want to manipulate my social network. Maybe it's me, maybe it's the temporal process, where basically a group grows by 1 member.
Okay.
I have a group of 3, in your language, call it as an undirected hypergraph of some cardinality. Now I'm adding a new member in the group, certainly completely fine operation. The bipartite graph is an absolutely well-defined graphical operation. I just simply make a new edge between an A and B type vertex. Now, in the hypergraph, now I suddenly have a hypergraph edge of cardinality 4, right? So it seems that the difference between the 2 is in one case, I do not pre-configure any cardinalities. I simply say I have a cardinality, perhaps finite, of each group, and then I can freely add or retract edges into that. On the other hand, if I do hypergraphs, I seem to explicitly track having the exact cardinality of a group. And now what I found interesting is that now if you count patterns, it is not at all the same thing of saying, is a group having at least 3 members? It's a different question than whether it has exactly 3 members. And so, I mean, maybe you are not realizing it, but it would perhaps be interesting to contrast the 2 things. In your experience with the data sets you had, was it really an advantage to be able to count in this way exactly groups with exactly 3 members? versus groups with at least 3 members. It's a different way of counting, right?
Yeah, no, in like, okay, this is like I think more a way, like a difference in the way we state problem with respect to a difference in the way we represent our data, in the sense that I think in the case of motifs, for example, you care about counting patterns with this shape. So the 6 patterns I have in these slides. So in traditional network science, the problem of motifs was stated like this, and it was very trivial to generalize to hypergraphs, and that's what we did, and that's why we stated the problem using hypergraphs. But
I'm not questioning your reason. I'm only saying it's an interesting observation that you say there's a advantage in this way of counting, because I mean the main question is, of course, typically your networks might come from a dynamic process or from temporal observations of data. And I mean, now it's really a difference. In the hypergraph setting you can say something like, I see a process where if I have a hyperedge of exactly 3 members, I can get a hyperedge of 4 with a certain frequency. In the other setting, you could say something more general. You could say, if I have a group that has at least 3 members, I have n members, then I have the threshold to do a transition. So now the interesting question is, in actual life data, maybe I should rephrase the question. Is it really that you see scenarios where it's advantageous to have this exact counting implemented with hypergraphs? I mean, is there data sets which are better modeled with these kind of hypergraphs than hypergraphs?
In my experience, I think they can be equivalent representation, hypergraphs and bipartite graphs, in the sense that it depends on how you see the problem, and the way you want to attack your problem can be better explained using hypergraphs or bipartite graphs, but you usually get the same results at the end. So it depends on how you define your operation on both. So yeah, for example, in this problem, I count hypergraphs, but on the back end in my software, actually I'm using bipartite graphs and I'm converting between the two. So from a narrative point of view, it's easier to represent the problem using hypergraphs, but like from, I think a representation from point of view modeling, they are the same, using at least like representing real world data. They are equivalent usually. And this is my experience, but.
No, I mean, mathematically, no, but I mean, apparently in your...
No, yeah, mathematically, I think they can be different, but like when you represent real world data, yeah.
What I mean is the way you count patterns is maybe the better question. And I mean, what you mean by an embedding of such a kind of hypergraph you're showing into a graph is probably that you count one hyperedge disregarding, as you said, you have a set. So you must have an algorithm which tries to complete somehow. You take one base vertex and you try to search, is it contained in some bag? And I mean, you don't count a match more times. I mean, it's not a monomorphism, it's something else. You just pick the set and don't count multiplicities. While if you had an hypertype graph, then it would matter in which order you match the edges, so you would get multiplicities that you would have to divide out again.
But that's why he said that how he encodes the order.
That's the point. Yeah.
Exactly.
Yeah, because
Sorry.
no, for me they have like a very specific name, the nodes. So a node is a unit in the system in a bipartite graph, and a node is an edge in the system. So in like my representation from like a structural point of view, like computer science point of view, this is equivalent, but like I think mathematical they can be very different. But if you, I think, label the nodes as unities and label the nodes and edges, and you fix your like semantic, they are equivalent.
But again, the key point is once fixing the data structure, you are fixing also the kinds of analysis you can do on temporal graphs at least. Because now you are essentially telling us, again, imagine you wanted to understand the functioning of a social network. Now you're pre-configuring that transitions you can have are necessarily of type hyperedge goes to hyperedge is the basic example. While in another setting, you might permit an analysis which says, on average, the statistics of the way a group grows is it has to have so and so many people exactly, or at least so and so many. I'm only saying that it's basically a question of what are you going to do as a type of analysis later, because you're only providing us with this way of pattern count, right?
Yes. Yeah.
Do you understand the question?
Yeah, it's really like task dependent.
Is it useful? Is it in social network analysis, for example? Is it in the temporal social networks, for example? Have you experimented with this?
Yeah, there is. Not me personally, but there is like a paper from these guys here, Jacopo Jacopini, that experimented with the temporal hypergraphs and group formations in hypergraphs. But yeah, the idea is basically that groups can grow in time and you can add one node to an interaction. For example, you start by an interaction of size 3 and you get a new node and it becomes an interaction of size 4. And they study how this happens in real world data. So yeah.
And it was really useful in that setting, not just, of course you can map. My difficulty is that I can, of course, take a bipartite encoding of the thing, where the process is really just take any group and, take any member, not yet part of the group, and add one single link between them in the bipartite graph. And from the outside world, it would look like I have a bunch of transitions. For each possible cardinality first, I get one more cardinality. I have to completely remove, so I have to make a new one. So these are two completely different encodings. And this could produce an artifact in the analysis, no?
But I don't know. I think it depends on the semantics you give to your bipartite graph and to your hypergraph. Usually, the way we use bipartite graph leads to, for the way we think about bipartite graphs, they are equivalent. So it's equivalent to add a new edge or construct, like saying that an hyperedge of size 3 destroys and creates another hyperedge of size 4.
I don't know, you probably missed the first my talk.
Yeah.
Yeah, so the interesting question we had there is that basically if you look at real-life systems which come from some sort of transition sequences on the states, like a social network evolving, there's some elementary operations involved, of course, but typically you see a bunch of operations having happened in observation intervals, so you have no idea what are the internals of. You could have the atomic transitions, but you see typically a compound transition of some sort. And then you might ask for a model that produces your data, right? Maybe some mechanistic model that says a certain sequence of transitions is necessary to form a supergroup or whatnot, And I'm asking more about the kind of experimental data that you have seen when working with this, that motivated you to pick this particular very sort of explicit coding of, let's say, degree structures and whatnot. Was it something that is really important in applications, or was it implementation-wise efficient?
What do you mean by applications, by the way?
I'm wondering if there's, for example, in people trying to model social networks.
Like what we were showing, Francesco, maybe you can show the paper of yours with Federico, like the one where you dissect, the one where you have motifs in social networks, in bio-networks, in authorship networks. And it seems to be indeed, if maybe he would be using your definition of this motif, that would be actually really using these patterns, one would dissect and they would fall into two different categories, social networks and the other, the non-social networks. The one from 2000?
Yeah.
Right, I think. Do you have maybe that kind of?
I'm only surprised because for example, in biochemistry, which is of course not social sciences, but there, for example, it was quite important that the kind of data structure that really models most of biochemical reaction is not technically just a hypergraph, but something where you have also a notion of sub-hypergraph, let's say. So a hypergraph where you can speak about a partial embedding, or the hyperedge is not fully specified, let's say. So it's actually akin to a certain version of hypergraph. So I was just surprised that hypergraphs in this particular way, just bags, seem to play a technical role in this analysis, which is interesting.
Yeah,
I think can I try to rephrase your question so to make sure that I understand and maybe to possibly make it clearer. Is it you're asking why or what data motivated the use of
advantage
of hypergraph over bipartite graphs? Okay.
Yeah, or like even this point Nicolas right? I mean, there were indeed like it's a bad way of putting that. But it seems to be that what you're saying that there would be also an extended number of ways to generalize.
Or said otherwise, on states, on complete graphs, I see immediately you can map one into the other. They have different features. I mean, as I said, subgraphs of a bipartite graph have exactly this feature that you can speak about a constituent in what would be a hyperedge otherwise. So I mean, you have a finer mathematical notion because you have more ways of embedding things, but for maybe the representation of the data, this could be precisely equivalent, of course. But then once you look at dynamical systems, you look how systems change and how, if you want to analyze how steps can occur between changes, this is an extremely different data structure, also mathematically. So because exactly of these differences in what you can call an embedding. So with a back hyperedge, you can speak about vertices that are incident to it, but you cannot say anything further. While with bipartite graph, you can speak about each of the ways an edge is incident, vertex is incident. So,
but what does it mean, like in a bipartite graph, to be incident for an edge? Because, like,
let's take a directed bipartite graph for simplicity. It is easy to say that if you have some type of vertices modeling groups, for example, and some others modeling elements in the group, then you can say, first of all, which element is part of the group by simply asking is a relationship. But then also you have to compute the cardinality of the group by counting the number of linked edges. While in your back model, it is just explicitly given, right? In the data structure, you favor a presentation where you directly know the total cardinality of that edge, hard to hold it. So while in the other setting, the group type vertices are just that. They're just a kind of vertex. You don't have any a priori information of what is the concrete degree of that. That only gets manifested once you are in a complete graph. And now if I look at manipulations of these, you do not have to break any structure at all. You don't have to remove these group vertices to add a new element. You can keep the exact same entity, just add a new link. While with a hyperedge, you would have to remove the hyperedge, make a larger cardinality hyperedge. You see what I mean? Right?
Yeah, but
And now if you try to come up with a model for a dynamical process that at its root does perhaps nothing else but changing group sizes, then one version in the bipartite world would have an extremely simple generator, which is just take two people, one of group type, one of element type, and link them or unlink them. This way you can get a dynamical process that can at random generate group sizes. Or you say the version in your language, which would say you have to get a list of possible transitions, one for each input degree of hyperedge. And then maybe you say, in my real life example, I only have ever degree 3 go to degree 4, maybe some selection of hyperedges. It's an extremely different analysis, right?
Yeah.
But, you see what?
No, but yeah, but I think, maybe like from a mathematical point of view, no, I mean, maybe there is like,
because this is very specific to the writing, right?
Yeah, I mean, I'm not really into like dynamical system, but the question, I mean, the way I understand the thing is that we don't really care about this usually in application, at least in the dataset that we have, for us is the same to represent a dataset using a bipartite graph and an hypergraph. And you can always state the problem or the task you want to analyze using both languages. For example, here, if we want to understand what are the most frequent patterns in a large hypergraph, I stated the problem using the language of hypergraph because it was easier to translate from the old problem in network science from graph to hypergraphs. But the same problem could be stated using bipartite graphs. And you add in that case frequent patterns of bipartite graph, and you could always reconstruct from like a small bipartite graph as a small hypergraph and vice versa.
I guess Francesco, that their models are sort of more intended for static representation, right?
I think that was my main question.
Yeah, I get it. I understand.
And also weighted versus unweighted. And we discussed a bit, Francesco, about the colored, non-colored, because in this case also these motifs could be, we could list them and dissect the network of hypergraph even more if this is needed.
Yeah, of course. The question is always if something is needed, because on top of hypergraphs, you can add a lot of information, like putting a single weight to every node in hyperedge to see how much every node contributes to the hyperedge. And in that sense, I think like what we were discussing, like of the difference between bipartite graph and hypergraph, they disappear when you have like a computational framework in a computer where you can add information and treat an hypergraph in the same way you can deal with bipartite graph and vice versa. So if you care of weights for every node that participate into an hyperedge, you can just add an attribute to a variable in a computer. You don't need like a bipartite graph. But I think from a network science point of view, you benefit from a clearer statement of the problems using hypergraph.
Yeah, in the talk before needs, I also discussed this question a little bit, just because indeed in the way you encode, it depends on how you can kind of recall the answer to your question when you define this representation of the hypergraph, because in a way that when you are starting from your social, technical, and coauthorship network, and I was putting your paper as an example of it actually, that in a way when you, depending on how you encode it, also then you will decide in the answer if your question will be different in a way. You kind of decide how much of the information you put and encode in the bipartite, in a line graph, or in a click graph, or in hypergraph. And I mean, sometimes there would be information reduced in this representation, right, of a hypergraph. I mean, I don't want to repeat, already we discussed it enough, I think. Yes, I mean, it's not, for me, it's just a comment, sorry, just for that. We will send you the recording.
It's on YouTube.
Yeah.
Okay.
So there's a question, maybe this further clarifies the discussion from my colleague at the Wolfram Institute, saying whether the hypergraph algorithms that you're running reduce to a bipartite graph with adjacency matrix representation and just linear algebra. And I'm curious about the details of how much, because exactly in this translation, so for example, I'm thinking about motif matching, just to count motifs, how you deal with, for example, redundancy of symmetry, and if you had these two representations, that would matter, right? When you do that kind of matching, if you had a sort of native set matching, or you had to actual click matching of the motif. So yeah, any insights on how you under?
Yeah. No, I think we have some like. I think different, sometimes interest in like the way we state problems. For example, in my case, motifs are just like patterns of sets in a data structure. So in that sense, I use multiple data structures as I need to store my data in a computer. And I use bipartite graph, but I also use adjacency metrics and so on to query efficiently my data structure depending on the subtask I need in my algorithm. That's why I was mentioning that in my way of seeing things, bipartite graphs and hypergraphs are the same, because when you put in a computer and you want to perform your task, basically, they are the same. And also my algorithm, for example, for counting motifs, is just like an iteration over sets and very efficiently the subsets in a larger database of sets. So yeah.
We were doing that also because in Python, also it's specificity of Python, right? That with sparse matrices, it's faster to do some things. This way.
No, it depends really on the subtask you want. Like I developed like my own data structure from scratch to have like consistent and multiple representation of the data at the same time. And for example, if you want to get the neighbors of a node, one data structure is more efficient than the other. So you don't, like, for example, you don't have like just to give an example, for this task I would use like maybe a bipartite graph and not a matrix, and maybe there are tasks in which I use vice versa for the same for other subtasks. So yeah, to deal with hypergraphs, I use multiple data structures at the same time. Each data structure captures different aspects of the data, and I can query fast what I'm interested in for the task.
Thank you.
One final question. Anyone? Specific? I wanted to just, out of curiosity, specifically what data structure you use for the algorithms for hypergraph isomorphism and the motif pattern detection and so on. Like, how do you deal with, for example, the redundancy of the symmetry? This is something that we are working on at the moment to encode more general data structures as edges in our own software. So curious to know how you deal with particularly the redundancy of the symmetry of a set with another set, because I imagine your elements are whatever characters, something that have unique IDs or something like that, or not necessarily?
Yeah.
Okay.
No, basically, in a very like naive way, in the sense that since I want to compute isomorphism between really small sets, I try every possibility and to see if there is one match.
Okay.
Yeah. Because I care more about like the feasibility of an algorithm for like an implementation point of view. I'm not really into like mathematical problem of isomorphism. So this was the most efficient way of solving the problem from like our specific task, and like also like time spent on writing code efficient point of view.
Okay, and so specifically, I mean, just to get a picture in my head how it works. How do you deal with just having permutations of the same? I mean, do you have a set specific match function that just out of the box, or you do something specific to deal with the permutation redundancy of a motif that is just a set? That's just a set.
Mm-hmm. Yeah, the idea was actually very I don't know how to say, very like programming idea, in the sense that I store every hyperedge as a list in Python, and each pattern is a list of lists, because in a pattern you can have multiple hyperedges, so you have a list of lists. And basically, if you sort your list in some way, you just need to look all the permutation for the IDs, but the sorting will remain the same. You just need to check if two lists of lists are the same after reordering and querying all the permutation.
Okay.
So, for example, if you have a list of one list of size 3 and one list of size 2 in Python, if you sort this list, they are reversed. So you will always have a list of size 2 and a list of size 3. So if you perform this sorting, whatever your list of lists is, you know that you have the cardinalities of the list sorted, and then you only need to check all the permutation for the IDs, and you will have that at some point you will have two lists of lists that are totally the same, and you just need to check.
Yeah. So my question then, basically, just to make it very concrete, do you have to basically divide? You define all the permutations and then you divide by the order of the permutation group, or do you do some kind of pattern matching that some canonicalization or something that allows you to basically not count all the matchings and just do one match per edge?
No, yeah, basically it's a form of canonization, but it's not very like formal. It can work only with patterns of size 3 and 4, because then it explodes. Yes, that's why I was mentioning that I'm not really into the mathematical details of the problem. We cared only on the feasibility from a computational point of view.
Okay, I see.
I mean, that was sort of my question, because of exactly this extreme explosion if you don't use other adaptive algorithm of n factorial analysis of permutations. I once heard, I'm not a social scientist, but I once heard that in realistic social networks, there's this pretty hard limit of 135 people who are sort of the largest social crowd you really interact with. So that is a high degree with 3. And I mean, also in chemical networks, we have the same problem. We might be limited for carbon by 4, but so that is okay. So when I would do a hypergraphs more for this whole matching would probably explode for me.
Yeah, but for example, in this case, the problem was actually to count patterns of size 3 and 4. So that's why we could do that, because it was by definition of the problem counting patterns of size 3 and 4, because the idea was to understand systems in terms of their decomposition in patterns of small number of nodes, and have a sort of fingerprint of the system. This fingerprint here, basically.
Okay. All right. Yes. Well, I think thanks so much, Francesco, for all the details. It's been a long day. Sorry for the delays, but yeah.
No problem.
And we'll see you everyone tomorrow at the same time. Thank you.